Well, I apologize for being late yet again. As the semester goes on, I sleep less and less and have harder and harder time getting up in the morning, I'll be honest. So, anyway, the I was going to try to put some guidelines about writing RO3s up over the weekend. I obviously did not get to that, but I'm going to try to do it in the next couple days, and yeah, I think that's pretty much the only thing I'd say other than a nagging reminder to turn in homework for so we can try to grade it in a semi-timely manner. Well, anyway, today we're going to discuss ANOVA, and I'll start just by giving a little motivation of why we care about ANOVA, analysis of variance. That, as you'll recall, a big focus of this class is when you have two variables or more than two variables and you want to analyze the relationship between them. Oftentimes you hope that one variable will predict or explain the other variable, and two of the big questions you want to answer in statistics are, if you see a relationship between x and y, is the relationship stronger than you would accept to see by chance? And just how strong is the relationship? How confident are you in your measure of association? So, quick review of different types of variables you can work with and what tests you would want to use in each situation. So I'll go over this again later because I found one of the common questions people have in this class is, okay, we've learned 10 million tests, how do I know which one to use on which data set? So, quick overview of that is if you have two categorical variables and you want to know is there an association between the two categorical variables, that if you have a drug and you have one group that gets the drug, one that gets a placebo, you want to know if they experience pain relief, yes or no. That's two categorical variables. Or do you want to know is smoking associated with lung cancer? You're either a smoker or a non-smoker, and you either develop lung cancer or you don't. Or you could look at the association between race and the risk of developing chronic pain after a car accident, a study that I was involved with. In each of these cases, you have two categorical variables. If you want to analyze the association, you can use chi-square tests or Fisher's exact test or proportion tests or things like that. And if you have one categorical variable that's binary and one quantitative variable, say you treat your mice with some type of growth hormone, either a treatment group or a placebo, and want to see if it has an association with the mouse's weight, or does smoking affect a baby's birth weight, or is there an association between metastatic and non-metastatic cancer and gene expression? In these cases, you can use a t-test because you're essentially, usually what you want to do is test the null hypothesis that the mean's the same in both groups. You can use a t-test, or in some unusual circumstances, you can use non-parametric tests like bootstrapping. Or if you have two quantitative variables, you want to say, is there a relationship between age and pulse rate, or time and infant mortality, or is there an association between the amount of alcohol you assume and bad cholesterol? In that case, you can use regression, either ordinary least squares or penalized regression, or some of the things like that. In this case, the important thing is that you have one numeric number and a second numeric number. You could possibly have one numeric number and several other numeric variables, and you want to know if this group of numeric predictors can predict the response, and you would use regression for that. And today we're going to do kind of a generalization of the t-test, where you have one quantitative variable and one categorical variable that's non-binary, that if you'll recall the insect sprays example from the first homework, or I guess that was the second homework, we had 6 different insect sprays and the number of insects that survived each spray. You want to test the null hypothesis that there's no difference across these 6 sprays. Or say that you want to evaluate the association between race and, I probably should have said, the risk factor of developing a certain disease. Say you want to see, is there an association between race and cholesterol levels, or race and blood sugar levels if you're looking at risk factors for diabetes or whatever the case may be. Or say you have cells on 3 different plates with 3 different treatments, you want to test the null hypothesis that they grow at the same rate on all 3 different plates. In that case, you would use analysis of variance, usually abbreviated as ANOVA. So what is ANOVA? Well, as I said before, it's basically a t-test when you're trying to compare 2 different groups. With the t-test, you're testing the null hypothesis that the 2 groups have the same mean. In ANOVA, you're testing the null hypothesis that 3 or more groups have the same mean. And actually, ANOVA works just fine even if there's only 2 groups, and you can show that it's actually equivalent to a t-test in that case, but it can be generalized to cases where you have 3 or more groups, as I'll show you here in a second. So why bother with ANOVA? Why not just do a bunch of t-tests? Rather than using this new method, you could just take every possible pair of groups, do a t-test comparing group A to group B, group A to group C, group B to group C, and so on down the line. And I mean, that might work in some situations, but there's various reasons why ANOVA is usually a better option. First of all, if you have a bunch of groups, this requires a ton of tests. If you have 10 different groups and you want to test the null hypothesis that all the groups are the same, you'd need to do 45 different t-tests. Aside from the fact that doing 45 different t-tests is a big pain in the butt, as we discussed a few weeks ago, your chance of getting at least one type 1 error is much greater than 0.05 if you do 45 different tests. So you would either have to control for that and lose power, or don't control for that and increase your risk of type 1 error. And it would be nice if you could just test the null hypothesis that they're all the same without either decreasing your power or increasing your risk of type 2 error. Or increasing your risk of type 1 error, blah. And there's other reasons to prefer ANOVA as well. First of all, as I said before, you get better power. That if you use ANOVA to test the null hypothesis that all the groups are equal, it turns out you have much better power to test that hypothesis than if you just did a bunch of pairwise comparisons. You can construct examples where you do the pairwise comparisons and none of them are significant, but the ANOVA is still significant. And another advantage of ANOVA that I won't go into in great detail in this class, that if you can take advantage of the group structure, that if you wanted to, for instance, test the null hypothesis that if you want to test the null hypothesis that what's an example of this? Oh, I was thinking of two-way ANOVA here. Let's say you have like both gender and race, and you want to test the null hypothesis that the means of the various groups are equal with respect to both gender and race. Then trying to do that using t-tests gets tricky, in particular if there's what you have interactions going on, which means that if you're, for example, a black female, then your risk of the disease is higher than it would be just taking into account the fact that you're black and female separately. That, I probably shouldn't even open that can of worms. We'll discuss this in much more detail on Friday, but for the time being, it suffices to say that if you have multiple categorical variables, that you want to test the null hypothesis that none of them are associated with this continuous outcome. There's no simple way to do it using t-tests, but it's easy to do using ANOVA. So, the ANOVA model, I'll write on the next couple slides. It isn't too crucial that you remember all these details, but it gives you the basic, but it's a good idea to know basically what's going on here. The basic ANOVA model is, say we have a bunch of different groups, and the observations are indexed by I, the groups are indexed by K. So the basic ANOVA model is the value of any given observation in your data set is equal to the overall mean that we call mu plus the offset for the kth group if observation I belongs to group K plus some random noise term. And under the null hypothesis, all of these taus are equal to 0. That is that the means of all the different groups are the same. That it's just equal to mu plus this noise term, that it doesn't differ from group to group. The alternative hypothesis is that at least one of these taus is non-zero, implying that the mean of that particular group is different from the means of the other groups. So, and it turns out that you can view ANOVA as a special case of regression, and personally, I prefer to think of ANOVA that way. And I mean, you can also define ANOVA in terms of sum of squared errors and a number of things like that. I decided not to even bother to teach that because, number one, I couldn't even remember that myself. I would have had to look it up. And I figured if I don't know it, there's really no reason to force you to know it. And number two, I mean, I just find it much easier to think of it as a regression problem. I'm much less likely to confuse myself that way, so hopefully it'll be less confusing to you. The other reason, as a side, why I've harped on regression so much this class is it turns out almost every single statistical test that we've covered in this class can be viewed as a special case of regression. So to a certain degree, if you master regression, you master everything you need to know in this class and elementary statistics generally. But, so at any rate, enough rambling about that. The way you can view ANOVA as a regression problem is you define a set of dummy variables. That basically a dummy variable means a dummy variable is equal to 1 if the ith observation is in the kth group and 0 otherwise. So if you take the example of like gender and race, you could have a dummy variable for gender that's equal to 1 if you're female and 0 if you're male. And you could also create a dummy variable for each race group. That there's like a Caucasian dummy variable that if you're Caucasian it's equal to 1, otherwise it's equal to 0. Similarly, you can create African American dummy variable that's 1 if you're African American, 0 otherwise, and so on down the line. And once you've defined these dummy variables, then to perform your ANOVA test, you can just fit a multiple regression model where you say the response variable y is equal to this linear combination of the dummy variables. And testing the null hypothesis that the mean is the same in every single one of these groups is equivalent to testing the null hypothesis that all of the regression coefficients are equal to 0 in this model. So if you look at it, it makes sense. If all these dummy variables are equal to 0, that implies that yi equals b0 for every single one of the k groups. That doesn't matter which of the k groups that you're in, the mean value is the same. On the other hand, if one of these b's here is non-zero, that implies that particular group has a different mean than the other group. Say this variable is for gender. If B2, if the coefficient for B2 is significantly different from 0, that implies that the mean for females is higher or lower than the mean for males, indicating the two means aren't the same and we can reject our null hypothesis. And if you were paying attention on the previous slide, you'll notice that there's no B1 or XI1. Why did we leave it out? Well, that's because, as you'll recall, we talked about this problem of multicollinearity and the fact that if one column of your regression matrix is a linear combination of the other columns, then there's no longer a unique set of regression coefficients. There's an infinite number of coefficients that will give a perfect fit to the model. That, say for instance, let's say you had a dummy variable for male and a dummy variable for female in the model. Let's suppose the means of the two groups are in fact the same. Well, you could have B1 equals 0, B2 equals 0, or you could have B1 equals 1, B2 equals 1, B1 equals 2, B2 equals 2. As long as the two B's are the same, it will give you the same predicted Y's. So there would be an infinite number of solutions in that case, which you don't want. So the way that you force there to be a unique solution to the model, you simply don't include one of the groups. So you just leave the dummy variable for male out of the model, use only the dummy variable for female. So the convention when you report these results is you choose a baseline group and then you compare all the other groups to this baseline group. Oftentimes you'll make the baseline group your control group. Then you can say that since you'll be comparing everything else to the control group, you can say things like the mean in the treatment group is 10 higher than it is in the control group. So an example of ANOVA comes from a student who was in this class a couple years ago that she wanted to measure the amount of GSH produced by her cells after 5 days in concentration, and I honestly have no idea what GSH is. That's just what it said on the spreadsheet that she sent me. Maybe some of you might know, but for the purposes of this class, it doesn't really matter. That basically she had 3 different groups, like a control group that was untreated, a vehicle group, which, as I understand it, it had some of the chemicals that were used to deliver the treatment, but it did not contain the treatment itself. And then the treatment group contained both the chemicals in the vehicle and the actual treatment. And she wanted to test the null hypothesis that the GSH concentration was the same in these 3 groups. As an aside, if anybody else ever has any data sets that they're working on that we could apply statistical methods learned in this class to, it will make me very happy if you email me and let me know about this. I really do try to come up with relevant examples for this class, but it's often more easily said than done. So when I get data sets from students that I can use in class, it makes me happy. But anyway. So I put a copy of the data set, of the file containing this data set on Sakai if anybody wants to try this example at home. But basically it had the data set was a spreadsheet with 2 columns. One column was called GSH, which was the GSH concentration. The second column was called group, which was just labeled as either control, vehicle, or treatment. And R is smart enough that if you have one column of numbers and another column of words, it's smart enough to figure out that the column of numbers should be a numeric variable and the column of words should be a factor. So it automatically creates a data frame with a column of numbers called GSH and a column of groups called group. So then we just fit the regression model as follows. We go summary, LM, GSH, twiddle, group. And this is another nice thing about R. If you give R a factor like group in this case, it's smart enough to automatically create dummy variables for each level of the factor. So in this case, as I said before, you can't have dummy variables for control, treatment, and vehicle because then the model wouldn't have a unique solution. So it automatically makes control the baseline group and then creates dummy variables for treatment and vehicle. And we can interpret this regression output just like we interpreted other regression outputs. The intercept in this case would be the mean GSH concentration in the control group, and the treatment and the coefficients for treatment and vehicle are basically the difference between the mean in these two groups and the control group. So in other words, that tells us the mean GSH concentration in the treatment group is about 2.3875 lower than it is in the control group. And in the vehicle group, it's about 0.11875 lower than it is in the control group. And the t-tests for both of these coefficients is strongly significant, indicating there's very strong evidence against the null hypothesis that the treatment group and the vehicle group have the same means as the control group. And the F statistic down at the bottom is going to be your ANOVA test p-value. The p-value that all these means are equal to one another is equivalent to testing the null hypothesis that both of these coefficients are equal to 0. Very strong evidence against that particular null hypothesis. And one quick aside, that it would be nice if R were smart enough to figure out that since you called it control, that's your control group and automatically make it your baseline group, but alas, R is not that intelligent. The reason that the control group got put into the control group is because it's first in alphabetical order. If your control group were not first in alphabetical order and you wanted to make it the baseline group, you could change the name of it from control to like underscore control or something like that to make sure it gets to the first of the alphabet. That's just a quick aside. And if you, in general in R, if you say LMY twiddle X, that will fit an ANOVA model assuming X is a factor, and R will automatically convert X to an appropriate set of dummy variables. And basically went over this before, that the control group will have a mean GSH level of 0.4475, which corresponds to the coefficient for the intercept. And samples in the vehicle group have a GSH level of 0.4475 minus 0.11875, and in the treatment group it's 0.4475 minus 0.23875, and both groups have a significantly lower concentration than the controls. And review of assumptions for ANOVA, that it's essentially the same thing as the assumptions for linear regression, only since all the data is categorical, it becomes a bit easier. Basically, the data has to be normally distributed. the data points have to be independent of one another, and the variances have to be the same in each group. This is quite similar to the assumptions we make for the t-test. And just like the case of the t-test, usually only the independence assumption will get you into serious trouble. That if your data isn't independent, the test will be invalid and there's basically nothing you can do to recover from that. If you've done homework 4, there's a problem that's supposed to help illustrate that. And the assumption of normality, just like in the case of the t-test, it's very rarely a big deal. If you have a really skewed data set with tons of outliers and your sample size is small, then you can get into trouble because of the normality assumption. But the vast majority of cases, if you have an even modest sized data set, then the central limit theorem will take care of the issue. Most of the time, you don't really even need to check for normality when you do this type of test. And the other assumption here is equality of variances. That, as you'll recall, one of the assumptions of linear regression is that the error terms or residuals have to have constant variance. If the residual variance isn't constant, then you have heteroskedasticity, which is my all-time favorite weird statistics word to whip people out to impress people at parties. But heteroskedasticity I guess it was Erica that went over this, can cause you to overestimate or underestimate the standard error of your model and cause the t-test or f-test to give incorrect results. And the same problem is potentially true in ANOVA, that if the variances of your groups are different, then you basically have heteroskedasticity going on, which can cause your t-test and f-test, in this case usually the f-test, what you care about, to be wrong. Now, in practice, thankfully, it's not that big of a deal. Most of the time your variances won't be precisely equal, and despite that fact, usually the results you get from ANOVA are just fine. The rule of thumb that you see in most textbooks is that if the ratio of the largest standard deviation to the smallest standard deviation is less than 2, then it should be safe to use ANOVA. If that condition is true, you're almost certainly fine. Even if that condition isn't true, which I don't think it is in Valerie's GSH data, you're still probably fine in most cases, but if your sample size is small and one group is much larger than the other, then you have to be careful, as I'll explain here in a second. But, like I always get ahead of myself on these slides, if the vast majority of the time, even if the ratio is greater than 2, it's usually not a big deal. That, first of all, if the sample sizes of the two groups are the same, that will almost always correct the issue. If the variances are roughly equal and the sample sizes are different, you're still okay. Usually the only situation where you can really get yourself into trouble is if the variance of one group is significantly larger than one of the other groups, and the sample sizes are small, and one of the groups is much bigger than the other, and you have one group with a small number of observations in that group and a large standard deviation, then that can mess you up. Thankfully, you don't have every single one of those things going wrong at once very often, but if you do have all those things going wrong, that's when you may want to consider non-parametric alternatives to ANOVA, there's tests out there in most textbooks. My opinion is they're anachronistic and you're better off using bootstrapping. I'm not really going to cover that in this class, but because as I said, in 95 to 99% of problems in real life, conventional ANOVA works just fine, so it's just not worth losing a lot of sleep over. So, in practice, most of the time people never even bother to check the equality of variance assumption when you're doing ANOVA because it's so rare for the problem to even be an issue. But if you happen to run up against a reviewer who decides they want to make your life difficult about this, then I'll briefly describe how you do it. As I said, I personally never bother to check this assumption unless I have a small sample size and with some groups larger than others. So one way to do it is to just compute the standard deviations directly. In the GSH data, I find the standard deviation for the control group, the vehicle group, the treatment group, and in this case it looks like the control group has the largest standard deviation, the treatment group has the smallest. I divide one by the other and it is in fact greater than 2. In this case, I'm not going to lose any sleep over it because number one, the groups have equal size in this case. Number two, we have a p-value of like 10 to the minus 10. So maybe the assumption's violated and our p-value is wrong, and maybe it should only be 10 to the minus 6 or 10 to the minus 7 instead of 10 to the minus 10. Do I care? Not really. That's the other thing. If your p-value is tiny, then it's usually safe to reject the null hypothesis, even if things are severely fouled up. It's only in these rare cases where it's a major issue. And if you'll recall in R, if you give the command y x equals in quotes level, that will return all the elements of x where x is equal to level. In this case, it gave us the GSH level for when the group, for the control group, the vehicle group, and the treatment group. Another way to do this is you can just plot side-by-side box plots and kind of eyeball it. That if the standard deviations are roughly the same, the IQRs should be roughly the same. Here you see that this does look like the standard deviations for the control and vehicle groups are noticeably larger than it is for the treatment group sort of thing. So that's potentially cause for concern if the sample sizes were unequal. And yeah, in general, if you go box plot y twiddle x and r, that gives you side-by-side box plots, which you should be familiar with if you've done homework too. And if you don't see any evidence that some IQRs are wider than others, then you can conclude that the ANOVA model is valid. And you can also do these scale location plots in R that I think Erica went over, where you plot a square root of the standardized residual against the fitted values of the regression model. If your variance is constant, this red line should be straight. Here, it's increasing from left to right, offering a bit more evidence that there may be some problems with this equality of variance assumption. And to get that, you just save the output of your LM object and LM.object, and then you apply the plot function. And if your ANOVA assumptions are satisfied, this scale location plot should be quote-unquote flat. If you see it increasing like did on the previous slide, that indicates your assumptions may be violated. And what if you want to do some pairwise comparisons within groups after you've done your ANOVA, and say for Valerie's data that we've tested the null hypothesis that the two groups are equal, and we've also compared both the vehicle group and the treatment group to the control group. But say you wanted to compare like the vehicle and treatment groups, for instance. Or you'll recall like the insect sprays example from homework 2 where we had the 6 different insect sprays. What if you had a problem, or what if you wanted to see which sprays were significantly different from the other sprays? The ANOVA output will only compare each group to the baseline group. You may want to compare some of the groups with one another. And one thing that makes this a bit tricky is that, as I said, you will be doing multiple cases in that situation, so you won't want to do just every single possible pairwise t-test, because that could potentially give you inflated type 1 error rates. So one way to get around this problem is to use something that's called Tukey's on a significant difference method. And to be completely honest, I don't even remember the details behind this method. I would have to go look it up. It's one of those things that I don't use often enough to really remember all the details for it, but I do have the R commands on this next slide, and hopefully that will be sufficient for this class and anything that most of you would ever want to do. It basically creates confidence intervals for each possible set of pairwise differences while taking into account the multiple comparisons. That these intervals are chosen such there's a 95% probability that they'll contain all the true mean differences, so you don't have to worry about the multiple comparisons problem. And the way that you can do that in R is to use the TukeyHSD command together with the AOV command. That basically, you already save it in an object called gsh.tukey and then spit out that command. And it shows the difference in means between each possible pair of groups, then the adjusted lower and upper 95% confidence bounds for these mean differences, and the p-values taking into account the multiple comparisons. We see there's fairly strong evidence against the null hypothesis that each of these different groups are equal to one another, and we can see like the difference between treatment and control is minus 2.3875, same as we got from regression. Difference between vehicle and control 0.11875 again, and if we compare vehicle and treatment, the difference is about 0.2. And you can also plot these differences that may be easier to visualize. If you go plot gsh.tukey, that will give you a set of plots that look like this. Any set of pairwise comparisons that crosses this dotted line is not significantly different from 0. In this case, nothing crosses the dotted line. We can conclude that all these groups are different from one another. And you may have noticed on this previous slide that rather than saying TukeyHSD of LM GSH twiddle group like we did before, I said TukeyHSD AOV GSH twiddle group. Why did I do that? Well, in general, TukeyHSD of an AOV object will create a set of confidence intervals such there's a 95% coverage probability for all the confidence intervals combined. If for some reason you want a different coverage probability other than 0.95, you could say TukeyHSD, comp.level equals 0.99. In practice, people almost always use 95. And what is this AOV thing? It's an R command that's specific for ANOVA that, I mean, you can try it for yourself with this data or any other data set that you have. it will test the null hypothesis the mean of y does not vary with respect to x. I prefer to use LM twiddle x for this because the f test at the bottom is exactly the same as the p-value that you get from AOV, plus LM gives you a bunch of additional information that AOV doesn't give you. It gives you the coefficient estimates, the p-values. For the various coefficient estimates, I just prefer LM for a variety of reasons. Unfortunately, if you pass an LM object to TukeyHSD, it will blow up. It has to be an AOV object, so you'll have to use AOV twiddle x instead of LM twiddle x. I don't think I have any problems on this in this class, so if none of that made any sense, don't worry about it, but just in case you ever want to do this for your own work. And it looks like the bottom of this slide got cut off when I converted it to Keynote. The full slide is on PDF if you want to see it. I think it just says, but it is needed for TukeyHSD. That last line got cut off. So, things to remember for today is you can use ANOVA to test the null hypothesis. 3 or more groups have the same mean. It actually works for when there's only 2 groups, although you can just use a t-test in that case. It can be viewed as a special case of regression if you define the appropriate dummy variables, and it depends on various assumptions, including this equality of variances, which usually isn't that big of a deal. It's actually independence that will really get you into trouble, but you can test for it if you need to. And if you want to look at pairwise comparisons between groups, you need to adjust for that. Something like TukeyHSD is the easiest way to do that. And here's the new R commands for today. Any questions about any of this? Okay, more on ANOVA on Wednesday.